All right, in this video, we're going to work through problem 4.192 from our book. It says, in the game of Yahtzee, 5 balanced dice are rolled. A, what is the probability of rolling all twos? Okay. All right. So we have 5 dice that are all twos, right? So we can write that like so. That's the probability that the first one is a 2, the second is a 2, the third is a 2, and the fourth is 2, and the fifth die is a 2. Okay, so we have a bunch of events that are joined by ands here. So the first is a 2, second is a 2, and third is a 2, and fourth is a 2, and fifth is a 2. So what we have to ask ourselves when we calculate this probability, right, it's a bunch of ands in there, okay? And so we have to ask ourselves, are these events independent or not? If I roll a 2 on the first die, does that affect the probability of rolling a 2 on the second dice? And the answer is no, right? It doesn't matter what you roll in the first one. The probability of rolling a 2, right, on the second one is still 1/6. And same thing with the third die, right? The probability of what you rolled on the first and second one has no bearing whatsoever. It doesn't affect or change the probability of the third one. So the probability of rolling a 2 on the third one, given that the first one is a 2 and the second one is a 2, is exactly the same as just the probability that the third one is a 2. So all of these events are independent, and that means that you can use the special multiplication rule. And the special multiplication rule just says all you have to do is multiply these probabilities together, right? So that would be the probability that the first one comes up 2 times the probability that the second one is 2 times the probability that the third one is 2 times the probability that the fourth one is 2 times the probability that the fifth one is 2. Okay. All right, and then each of those is 1/6. The probability, right, of the first one being a 2 is 1/6, and the third one, and the fourth one, and the fifth one. All right, so that comes out to be 1/6 to the 5th power. That's 1 over 1296, right? If you multiply across the tops, you'll get 1. If you multiply across the bottoms, you'll get 1296, right? So that's the probability of rolling all 2s. And there is nothing magical at all about rolling all 2s here, right? It's the same probability, right, for rolling all 1s, for rolling all 3s, for rolling all 4s, and for rolling all 5s and all 6s, right? All of those would be the same. And that's important because you're going to need that in the second part. So there's nothing magical about the 2, right? On these, you would do them exactly the same way, right? The probability you get all 1s is the same as the probability that the first is a 1, and the second is a 1, and the third is a 1, and the fourth is a 1, and the fifth is a 1, okay? And then those are independent, just like we argued about before. The outcome of the first die does not affect in any way the outcome of the second die, right? So you can multiply all these together, and the probability of rolling a 1 is also 1/6, right? And so it's the same for all of these. All right, so that's part 1, or part A rather. And part B, what they want to know is, what is the probability that all the dice come up the same number? All right, so I'll write that as all the same. So we want to calculate the probability of all the same. And so what we'll have to do is write that in terms of some other events using ands and ors, right? So what that would be is the probability that we get all ones or all twos, right? Or all threes or all fours or all fives. Okay. So this time we are calculating the probability of a bunch of ors of events. Here we are calculating the probability of the ands of a bunch of events, right? And we said, hey, these events are independent, so we can use the specialized multiplication rule. Well, this goes back to a previous section, right? Here we are calculating the probability of the ors of several events, right? And so we need to ask ourselves, are these events mutually exclusive? Is it possible that in a single roll of 5 dice that you roll all ones and at the same time roll all twos? And the answer is no, right? These events are all mutually exclusive. Now you can't, none of them can happen at the same time as each other, okay? Any of the others. So that means that we can use the specialized addition rule that says that this is going to be the probability of all ones plus the probability of all twos plus the probability of all threes plus the probability of all fours plus the probability of all fives. Okay, and so we can add those together, right? So all ones we already talked about is 1 out of 1296. And the probability of all twos, that's what we calculated in part A. All threes, all fours, and all fives. All right, and that comes up to be, all these have the same denominator, right? So if I add across the top, I get 6 over 1296. Okay. All right, and that is it on this one.